guys, I'm going to give you the answers to this. I'm going to go over them. You guys can watch this if you want. When I'm grading, I'll just kind of tell you which ones are wrong and then send you the link to this. So if I'm answering the following here, it says, what is the melting temperature of the above substance? Well, in my notes, I did water, and my water looked the same like this, only it was 0 and 100, because that is the melting point and the boiling point of water. All right, so this is obviously some other type of substance. So what is the melting temperature? Well, the melting temperature this is still melting right there, so it is 5. What is the freezing temperature? Well, remember, it's melting if I'm going up, it's freezing if I'm going down, but it's all at that line there, so 5. What is the boiling temperature then? So if I'm looking here at this plateau, that is boiling, just like this is boiling for water, and that is 15. All right, so now let's look at number 4. It tells you that E represents a gas that is being heated, right? Because right here, I am a gas now, and as I go up, it's just a gas that's being hotter and hotter. Okay, so let's look at the rest. It wants us to say what A is, and basically A is ice that is getting warmer. All right, because this is a heating curve. We're increasing, we're going up, our temperature is. So then when you look at B is this plateau, and we are, at this point, we're melting because we're getting hotter, right? So melting. Now remember, just because I could bring a piece of ice out into the classroom right now, sit it on the desk, and it doesn't like it instantaneously all is melted. Like it slowly happens at a certain temperature. So it's not like bam, it's all gone. At B, we have some that is still ice, we have some turning into liquid. But C is where we should all be complete liquid. So liquid, heating up, right? Because we're going up. Our temperature is increasing. So C is where our liquid is heating up. And then finally D, you get where evaporation starts. If this were a cooling curve and I was going down instead of up, it would be like condensation happens, so my gas turns into liquid, my liquid's cooling down until eventually it's freezing, and then it turns into ice. All right, number 5, it says, in which section of the graph are atoms moving the least? Let's see here, moving the least. All right, so think about this. It's either solid, liquid, or gas. Gas atoms are bouncing around like crazy because gases are warmer. Gas is kind of, if I exhale like right now, the air I just blew out is going all over the place. It's not like it stays in this uniform little hard ball that goes around and hits people. All right, but solids are uniform. They are not moving hardly at all. I mean, they move. All atoms are constantly moving. But if it's solid, yeah, that's not moving a whole lot. So my solid is at A. Number 6 says, in which section of the graph is the substance all liquid? Well, all liquid is going to be C, right here. Now, number 7, it wants me to label, so I'm going to erase some of this that I've written on. It wants me to label melting begins, so my melting begins right there, about right there. And then it says melting complete, so right here on the other side of that bin, it's complete. And then boiling begins is about right here at the very beginning of that bend. All right, so that is that page right there, this participation points. Now I want to go over 10.6 number 1. I'm just going to go over a few of these with you. So number 1, this substance has no definite volume or shape. So once again, it's either gas, liquid, or solid. But no definite volume or shape, that's going to be a gas, right? Gases don't have a shape. When I just exhaled, it just went all over the place. B, the particles in this substance do not interact strongly with each other. So that means that if they're interacting strongly, that means they're close together. Which, if they're not interacting strongly, that is a gas. Gas particles will go as far away from each other as they can. They spread as far as they can. C, the particles of the substance are held in a definite structure. A definite structure, like the pen I'm holding in my hand right now, is a solid. Or ice. ice. Think of an ice cube. Ice cube has a definite structure. D, the particles of the substance are held in a definite shape of the container. So think about this. If I put ice in a cup, it's not the shape of the container, but when it melts to water, it's the shape of the container, and the gases just escape. So this one is liquid. E, the particles of the substance are very far apart. Once again, a gas. This substance occupies the entire volume of the container. Now, this one has tricked more people than the others, and that's because a lot of them think it should be liquid. And yes, a liquid will occupy what it is, but if you have a bottle that's a water bottle that's only half full, the water is only in the bottom half of the bottle. Now, if I take that same water bottle, empty it, and blow a bunch of air into it, that air is it fills the entire bottle. So this is a gas. Most of these are gases. All right, so number 2. Let me grab this out so I don't have to do my calculator over and over. I think I got the answers here somewhere. Yeah, here we go. All right, so number 2, it just wants to know calculate the heat. So the big thing is we are at 0 degrees Celsius, which means we're using that 334 number. So for A, now remember we have that curve that goes like this, and at 0 degrees, we took our mass times 334. So that's what we're doing here. We're going to take 65 times 334, and that is 21,710 joules. B, I'm going to take my 17 grams of ice and multiply by 334 because once again, we're still at 0 degrees Celsius, and this is 5,678 joules. Okay, so now absorbed versus released. Now, if you are melting, you're absorbing heat, right? You're absorbing heat, it makes you melt. So these both are melting, so these are both absorbing energy, heat energy. All right, let's look at C. It says 225 grams, so there's my grams, and I'm still at 0 degrees, so 334. Now this is 75,150, or they want this in kilojoules. If you notice here, kilojoules, that means you're going to move that decimal 1, 2, 3, 75 kilojoules. Now you are freezing, so you're not absorbing. If you're absorbing heat, you're getting hot. This is freezing, so I am releasing energy. All right, D, I have 50 grams of water. I'm still at 0 degrees, so still at 334. 16,700 joules, or they want this in kilojoules. So I'm going to move that decimal point 3 spots over, and it is 16.7 kilojoules. And once again, this one is freezing, so it is releasing energy, that heat energy. Okay, I'm going to go to number 3. Number 3, everything is at 100 degrees Celsius, which means I'm using that magic number 2,260. So for A, I have 10 grams, and remember, at this, when we're at 100, it's just mass times 2,260. So I'm going to take my 10 grams, I'm going to multiply by 2,260. That's going to give me 2,600 joules. All right. B, it says 50 grams, but once again, I've got to multiply that by 2,260. That is going to give me 113,000 joules. Now, if you notice, they asked for kilojoules, so I'm going to move that decimal 3 spots over. And real quick, to the absorbed versus released. Same thing here. If I'm vaporizing, that means I'm getting so hot that it's turning into a gas, which means I am absorbing heat. All right, C, I'm going to put up here. It says I have 8 kilograms. Now this can get people. 8 kilograms. So when I'm going to kilojoules, notice how I move 3 spots over. So if I want to go from kilo just to regular grams, I'm going to go 8 spots over. So this is really 8,000 grams times 2,260. And that is going to give me, gosh, it's 1.8 times 10 to the 7th, I believe, joules. And we are condensing, which means that it's like when you're in a steamy shower and it's gas and it hits the cold mirror and it condenses to form water. So that's what's happening here. So you are releasing energy, you're getting colder. Now then D, we have 175 times 2,260, and that is going to give you 395,500 or 395.5 kilojoules. Because that's what they're asking for, kilojoules. Once again, this is condensing, so it is releasing that energy. All right, number 4 is going to be the most important because our next homework assignment that is for a grade is going to be based off of number 4. So I always draw these charts. So when I read this, joules needed to warm 20 grams of water at 15 degrees to 72 degrees Celsius. So I'm like, okay, and I don't always draw the full-blown chart like this. I'll just say, I know that it's going to be on this, so 15, 75. I know it's going to be that diagonal line. So I'll just draw the diagonal. Now on the diagonal line, we saw where we need mass, which is 20, times 4.184, the specific heat of water, times temperature change. So 70, let me see if I have my temperature change written down somewhere, 57. So 75 minus 15 is 57. And this equals 48, if I round, it's 4,800 joules. You may get 4,769. I just went ahead and rounded up. On B, I'm at 0 degrees and I warm up to 65. So I'm going to have 2 steps. That's why I draw this. Right away I know I have 2 steps. I've got the 0 degree line. So that magic number is 334 times my mass of 50, which is going to equal 16,700. Now this part right here, I've got my mass of 50 times 4.184, the specific heat of water, times my temperature change, which is 65, and that is going to equal 13,598. So now I'm not done. I need to take both of these numbers and add them together. So I'm adding them together, and my total is 30,298 joules of energy for water to go from 0 and heat up to 65. All right, that is it. If you have any questions, let me know, and the next worksheet will be for a grade, not participation. So let me know if there's anything you need. Have a great day. Bye.